Welcome back. Today, we're tackling a subject that is literally the lifeblood of process engineering, even though it mostly happens completely behind the scenes. We're going to demystify the highly technical but incredibly crucial process of line sizing in this explainer. If you've ever found yourself wondering how on earth engineers ensure that thousands of gallons of volatile chemicals, superheated steam, or heavy slurries move safely from point A to point B without blowing a gasket, well, you're in the exact right place. We're going to build a mental blueprint to solve this fundamental engineering challenge together. So let's just quickly get our definition straight. Line sizing is the process of selecting the appropriate pipe diameter to transport the required flow of fluid safely, economically, and efficiently. Notice those last three words. I mean, sure, anyone can just pick a giant pipe that will definitely carry the fluid, right? But that's going to totally bankrupt the project. On the flip side, if you try to save cash up front by picking a tiny pipe, it might literally explode under the pressure. It's all about finding that absolute mathematical sweet spot. Okay, let's dive into this. Line sizing isn't just flipping through a catalog and picking a tube. It's a massive, high-stakes balancing act. We have to meet the flow requirement, obviously, but we also have to limit the velocity of the fluid, meticulously control the pressure drop, avoid erosion and pipe shaking vibration, and above all else, ensure pump safety. If we drop the ball on any one of these goals, we aren't just looking at an inefficient system, we're looking at catastrophic real-world failures. To tackle this, here is our blueprint for today's explainer. We'll start with the stakes of line sizing, jump into the core math and formulas, walk through the actual 8-step design workflow, calculate crucial pressure drops, check out special fluids and edge cases, and wrap up with the common sizing mistakes you absolutely need to avoid. Let's move to section 1, the stakes of line sizing. Why do process engineers spend years mastering this? You see, there's this core tenet in engineering. Line sizing is a balance of hydraulics, safety, and economics. If your pipe is too small, your fluid velocity just skyrockets. That creates massive friction, which leads to huge pressure drops. Now your pumps have to work overtime, wasting energy. And worse, that high-speed fluid can literally erode the inside of the pipe or cause severe vibration. Or, think about this. If a pump gets starved of fluid because the suction line is sized wrong, it causes cavitation. Those are tiny, violent bubbles exploding against the metal, absolutely destroying your equipment. Like I said, a really delicate, high-stakes balance. Section 2, Core Math and Formulas. Let's look at the foundational physics that actually make this possible. Everything kicks off with the continuity equation. Q equals A times V. It looks simple, and honestly, logically, it is. The amount of fluid flowing through a system, that's Q, our volumetric flow rate, simply equals the cross-sectional size of the pipe, A, multiplied by how fast the fluid is moving, which is V, our velocity. So if you shrink the pipe area, the fluid has to speed up to maintain that same flow rate. Now, if we use some basic geometry to swap out the area for the diameter of a circle, we can rearrange that continuity equation to get our golden key, the required diameter formula. D equals the square root of 4Q over pi times V. If we know how much fluid we need to move, and we know the safe speed limit for that fluid, this formula spits out the exact theoretical diameter we need to start our design. Section 3, the 8-step design workflow. Because we know engineering doesn't happen in a purely theoretical vacuum. You can't just order a mathematically perfect pipe with a diameter of, say, exactly 4.127 inches, right? We have to use standard manufactured sizes. So, here is phase 1 of the real-world workflow. Step 1, get your process data, flow rate, pressure, temperature. Step 2, select a preliminary velocity based on safe industry standards for that specific fluid. Step 3, plug those into our golden formula to calculate the theoretical diameter. And step 4, take that theoretical number and match it to the nearest standard manufactured type size, which we call the nominal pipe size, or NPS. So the crucial point is what happens next in phase 2. Because we had to round our pipe size up or down to a standard NPS, our initial math is now slightly off. Step 5 is absolutely critical. We must recalculate the actual velocity using the pipe's true internal diameter, or ID. Then, step 6, we calculate the friction and pressure drop. Step 7, we check all of this against our safety and equipment criteria. If it passes, great. Step 8, we finalize and document. If it fails, we go right back to step 4, pick a new size, and try again. I mentioned earlier that we select a preliminary velocity based on the fluid. To really understand how vastly different these limits are, just think about water versus steam. Water is heavy, it causes a lot of friction, so we keep it slow, usually between 1.5 and 3 meters per second. But steam? Steam is light and compressible. You can safely rocket that through pipes at 20 to 40 meters per second. Compressed gases can easily hit 20 meters per second or more. You really have to know your fluid inside and out. Moving on to section 4, calculating crucial pressure drops. Because fluid naturally resists moving. Your total pressure drop, represented by delta P, is basically the sum of several thieves stealing energy from your fluid. First, you've got your major loss, which is just the sheer friction of rubbing against straight sections of pipe. Then you have minor losses. These occur every single time the fluid has to squeeze through a valve, turn a 90-degree corner, or pass a fitting. Finally, you have the equipment drop, as the fluid literally fights its way through things like heat exchangers or filters. You absolutely must account for all of it. To figure out exactly how much energy straight pipe friction steals, engineers rely on something called the Reynolds number. This helps us understand the fluid's physical behavior. If the Reynolds number is under 2300, you have laminar flow. Basically, the fluid is moving smoothly in neat parallel layers. But if it's over 4000, you have turbulent flow. It's chaotic, mixing, and swirling. Knowing this state is essential because it dictates which complex mathematical charts we need to use to calculate the pipe's friction factor. To put that friction into perspective, let's think about a standard engineering example. Imagine moving water at about 2 meters per second through 300 meters of a 5-inch pipe. The pressure drop calculation for that yields a massive number, 113,000 pascals, or about 1.13 bar. That is a huge amount of pressure totally eaten up just by the friction of the pipe itself. Your pumps have to be strong enough to overcome that massive physical force just to get the fluid to the finish line. Section 5. Special fluids and edge cases. Standard calculations are great, but the real world is messy. And this brilliantly illustrates why we have to be adaptable. Take standard pumps, for example. We have a single pump moving a single fluid. Yet, the suction line going into the pump requires a completely different sizing strategy than the discharge line coming out. For the suction line, we must keep the velocity incredibly low, between 0.5 and 1.5 meters per second, to minimize pressure drop and avoid that destructive cavitation. But on the discharge side, the pump has added huge pressure, so the fluid velocity can safely be much higher, though we obviously still have to watch out for erosion. Then we have fluids that break the standard rules entirely. If you're sizing a line for a slurry, say a mix of water and heavy mining rocks, you can't let the velocity get too low, or those rocks will settle and instantly plug the pipe. You have to stay above a critical velocity. Gas lines, they require totally different equations to account for the fact that gases compress and change density based on temperature. And gravity lines, like drains, don't even run completely full. That means we have to ditch standard pressure formulas altogether and use something called Manning's equation. All right, section 6, common sizing mistakes to avoid. We've built an incredibly solid blueprint today, so let's focus on protecting it. First, a vital reminder. Process engineering is a highly regulated field, and for good reason. Lives are literally on the line. Your sizing calculations, velocity limits, and material choices don't just come from thin air. They must strictly align with heavy-duty industry codes. Standards like ASME B31.3 for process piping, ASME dimension codes, and various API standards for oil and gas are your ultimate rulebooks. Always double-check your math against the prevailing codes for your specific industry. Finally, let's rapid-fire the most dangerous pitfalls we see in line sizing. Number 1, ignoring the overall pressure drop, leaving your pumps totally underpowered. Number 2, and I literally cannot emphasize this enough, using the nominal pipe size instead of the true internal diameter. A 2-inch standard pipe does not have a 2-inch internal opening. It depends entirely on how thick the steel walls are. Confusing those two will completely wreck your velocity calculations. Other killers include ignoring how fluids change density with heat, forgetting that every single valve steals pressure as a minor loss, and neglecting to check both the minimum and maximum velocity limits. So, as we wrap up our explainer today, I'm going to leave you with this question to ask yourself on your very next project. Have you meticulously accounted for every minor loss, true diameter, and fluid variable? Or is your line design inadvertently setting the stage for a critical system failure? Armed with this 8-step blueprint, you've got the tools to ensure it's the former. Take this methodology, double-check those internal diameters, and design with total confidence. Thanks for joining me today, and keep learning.